Hello everybody, it's Philip from Fundamentals of Physics 1501, and this is our physics video demonstration. Our instructor is Jay Murphy, and of course my field of study is mobile development. Today we're going to talk briefly about inertial scrolling and what it is and how it works. So many of you, if you have an Apple or Android device that's relatively new, are familiar with inertial scrolling, or what Android calls kinetic scrolling. It's where you can flick a scroll view, web view, or any other data view on the phones, and it continues to scroll after you let go and then eventually slow down. It's a wonderful way of scrolling through long lists, and it's become the standard in most types of software games and application interfaces. This is a game that we have up called GOTUS, and I'm going to show you how it works in here as well. So if I just move my fingers across the screen, I'm doing a basic scroll, which means that the computer game itself is capturing where my fingers are located at. It's comparing what the X and Y values of where I stop moving it at and where I start moving it at, and then it moves the screen appropriately. But if I want to get to a farther place faster, I can just flick from left to right, top to bottom, and it continue to move. So I'll show you that now. And so as you can see there, I let my fingers off the phone as soon as I flick. So I'm going to flick and let go, and it controls where it goes pretty quickly. It's a good way of getting where I want to go. The more I flick, the more distance I flick, the faster I go, the smaller I go. So how exactly then does that work? So illustrating this purpose will be my son Toby. Say hi.
Hello.
Helping me with this little experiment. So let's go ahead and set up the board here. As you guys probably remember from your high school physics class, whenever you slide something across a surface, it will go for a while and then eventually slow down.
And then stop.
Okay, and it does this because of the concept known as friction. And so the more force that you import, the speed will eventually slow it down. So let's go ahead and have him flick one of the coins.
And then
Ready?
go.
And go. Perfect. Now he'll flick another one. Now he'll flick another one. And that went all the way over here. So what we see is, depending on how you're flicking, each one can have a different location. Like this one went about 650 millimeters. The quarter went approximately 120. And the nickel, she went approximately 185 millimeters. And so as we flick them across the screen, they do eventually slow down, no matter what we do. And we need to know this because when we start, we need to control where we start, how far we flick it, and where we let go. Because that's going to help us measure our point of contact with the screen, our initial position, our second position, and where we let go. The distance between the two will represent the acceleration or the force that we put on the screen as we go across. And by that, we can calculate our acceleration and velocity, and we can calculate where it's going to scroll the rest of the screen to. So depending on how much we flick down here, if we flick really hard, it goes really far. If we flick really little, it goes very little. And that's exactly how the kinetic scrolling is going to work. So the math-wise, we talked about, where we're going to start on the screen, where we're going to go, and this is what's going to help us, understand the physics behind it. So knowing where we are, the target position at a given point, so the position at a given time is equal to the target position minus the amplitude times the exponential of the negative current time divided by the time constant. And the time constant in this case is about 325 milliseconds. Most new phones will use 325 because that's what Apple's uses to get about 60 frames per second resolution to figure out how far you're actually moving your finger so we're not making the screen jerk left and right as we're scrolling. And what that actually allows us to do is, as soon as we know our positions, we get a nice little curve like this. And this curve shows us our top position. So the time at the position is 1 minus the exponential of our time divided by 325. So we let go right over here in the corner is where we let go. And then it immediately accelerates. So we have a good fast acceleration all the way up through here. Our curve starts to decelerate around 340 milliseconds, around 810 milliseconds. It's just about done scrolling, so you'll see a physical slowing down a lot on the screen. And then around 1630, we're at right around 149 frames here. And it actually stops scrolling altogether because there's no reason to continue. So the curve is nice and exponential here, depending on how much force we impart. And so here's another brief demonstration of what that type of acceleration will look like. I'm going to put my finger up here on airplane mode, and I'm going to flick it up to the top of the screen, so right where settings is, and I'm going to let go. Notice that it didn't go very far. It did go far enough to move the scroll bar down so we can see things, but it didn't go very far, so let's move back up. So this time I'm going to move my hand all the way down to notifications and flick it to the top of settings and let go. And we see that in this case, it went significantly far. In fact, it looks like it went just about halfway down the screen. Because we imparted more force, our amplitude in this case was actually quite a bit farther. So we had a higher amplitude, which made it actually go farther in the end. So that, in effect, is how we measure the kinetic scrolling on an iOS device. Hope that made sense. You guys have a great day.